It was already a remarkable moment when NASA unveiled newly taken photos of the interstellar comet 3I/Atlas, now shining in a bright green color, a stark contrast from the deep red it once showed. That change caused ripples in the world of astronomy, heightening the mystery of the wayward visitor and fueling concerns over what concealed forces or unexplained chemistry could be at play within it. Scientists were swift to observe this change was not only an aesthetic event, it implied that mechanisms outside the realm of cometary models were occurring. As 3I/Atlas descended further towards the Sun, scientists everywhere rushed to interpret what was taking place, most disturbed by what the meaning of this color evolution could be. 3I/Atlas has fascinated astronomers since its discovery on July 1, 2025. It made it only the third verified interstellar object ever seen, after Oumuamua in 2017 and Comet Borisov in 2019. Its path, speed, and hyperbolic trajectory clearly mark it as a visitor from outside our solar system, an object that will move through and ultimately leave, as opposed to being gravitationally captured by the Sun. For months, its activity seemed normal, an expanding coma of gas and dust, slow brightening, and the formation of a weak tail as solar heating increased. But that dramatic color change from red to green was not normal. Previous measurements by NASA's Atlas Photometric Network indicated the comet's color index, ratio of blue to orange-red light, slowly evolving from a reddish color towards a more neutral or solar-like tone. Astronomers initially thought this was due to sun exposure of more sun-kissed, fresher material below a reddened surface as frozen grains started venting. Yet as the comet traveled further inward, spectroscopic and imaging measurements detected a more sudden change. The coma's glow, which was initially only neutral, suddenly and brightly turned green. One instant the comet's halo was red, the next instant it shone green, a momentary contrast that had astronomers trying to solve a mystery far more profound than mere color. Why green? For most solar system comets, a green color is typically associated with diatomic carbon, C2, which glows when it is exposed to solar ultraviolet radiation. But with 3I/Atlas, spectroscopic examination did not catch any intense emissions from the predicted carbon molecules. Rather, researchers saw cyanide, CN, radicals, and even nickel atoms within the outgassed products, a combination to be expected nowhere. The presence of nickel, especially, was disturbing. Comets in most cases exhibit metals faintly, if at all, and never in intensities enough to affect overall hue. More unsettling was the nonlinear behavior of these emissions. A few analyses indicated the release of these elements grew superlinearly, much more rapidly than simple temperature scaling would have predicted, meaning there had to be a threshold effect or switch-like activation process within the comet. This nonlinearity challenged the expectation that a comet's response to solar warming would still be gradual and predictable. This red-to-green transition was accompanied by the appearance of an optically visible anti-solar tail and a flattening of 3I/Atlas brightness curve. Prior to the transition, its brightness rose quickly as it approached the Sun, as expected if dust was being aerosoled from a reddened surface. Subsequently, its light curve flattened, indicating that it was now small icy particles instead of coarse red dust that were doing the scattering. Other models suggest that in its initial trajectory, the comet shed dust grains colored red by degraded organics or tholins, products characteristic of far-off, icy planets. Then, when the solar warmth increased, more strongly sublimating volatile ices released transparent ice grains into the coma and shifted the composite color toward green. But to most scientists, this dust and ice explanation is short of accounting for the suddenness of the shift. One of increasing concern is that underlying physical or chemical processes could be unfolding, processes that traditional cometary theory cannot account for. If 3I/Atlas contains volatile substances or buried material that is different from those in typical comets, we might be observing the activity of a whole new category of interstellar body. Exotic ices in the comet may lie in wait until a certain temperature threshold is passed, at which point they explosively emit bursts of material. The greenish glow might be a hint of these compounds being released, maybe from buried reservoirs that stimulate in random spurts. Another concerning hypothesis is that the internal structure of the comet provides for abrupt heat or pressure propagation, creating cascades of activity and sudden optical variations. If the outside crust is an insulator, sunshine could be heating up under the crust until it erupts through fractures or vents, bringing fresh volatile regions to light. Such a process could account for spatially disordered and temporally discontinuous color variations seen today. Scientists worry that the age of slow, steady brightening is gone and that we are seeing sudden discontinuous jumps in behavior rather than smooth changes. The occurrence of nickel in the coma is a second warning sign. The metal vapors are unusual to the forefront in comets and are usually only trace constituents. In 3I/Atlas, however, the intensity of nickel signatures suggests active metal-containing compound decomposition or maybe metallic complexes sublimating more typical of planetary materials than usual comets. If this metal comes from within the nucleus instead of surface contamination, it suggests a surprisingly heterogeneous internal composition. The association of nickel with cyanide emission suggests unusual organometallic chemistry or the existence of rarely volatilizing mineral phases typical of very few solar system comets. Such discoveries open up a disturbing possibility. 3I/Atlas is not a passive ice body. It might contain internal energy gradients, fossil radioactive heating, or buried volatile reservoirs, which induce bursts of chemical change. If this is so, it would revolutionize the current understanding of the assembly, processing, and preservation of interstellar objects over cosmic timescales. The other possibility scientists are examining is optical depth variation inside the coma itself. As outgassing increases, the atmosphere of particles surrounding it can get dense enough to change the manner in which light scatters and absorbs, possibly hiding or enhancing some wavelengths. Then, the color change could be non-chemical but an effective radiative transfer due to intricate interactions between the coma. However, in order for this mechanism to happen, there would have to be a finely calibrated set of particle density, size distribution, and optical thickness. This type of tipping point behavior disturbs theorists because actual cometary comas evolve more smoothly and predictably. Adding to the puzzle, 3I/Atlas's color change occurred in perfect synchrony with a discontinuity in its light curve slope. Prior to the change, its brightness rose steeply as it drew closer to the sun. Subsequently, the rate of brightening tapered off, implying a basic change in the character of its coma. Whether it is indicative of a shift in dust-forming rates, particle size distributions, or gas versus dust emission balance is unclear. Others speculate that the comet made the transition from a dust-scattering regime to one controlled by icy transparency. Others suggest the explanation might be deeper, that volatiles beneath the surface started to assert control as interior layers heated, supplanting the emission profile of the surface crust. If so, the color change would be a dramatic reorganization of mass loss, unveiling a composition and structure unlike any previously seen comet. Heightening the mystery still is that 3I/Atlas's behavior doesn't resemble its interstellar ancestor, 2I/Borisov. Borisov's behavior was mostly in line with what is known about cometary behavior, steady outgassing, orderly tail formation, and spectral signatures that match typical molecules such as C2. But 3I/Atlas seems to be defying expectations. Its change of heart isn't a subtle greening at perihelion, like in most comets, but rather a surprise mid-cruise transformation, changing color suddenly as it makes its approach towards the sun. This turns 3I/Atlas not just another star visitor, but possibly a messenger of unseen interstellar chemistry, redefining everything we believed we knew about comets and the processes that form them.